Okay, welcome to Deep Learning Classics and Trends. We're just talking, I think this is our eighth year of running DLCT. We rarely record, but I don't know, when the talk is this good, gotta save it for the future for posterity. So Tan here today is talking to us about, I think mainly this paper, Doc-to-LoRA, but in the title of Hypernetworks in the Age of LLMs. Take it away, Tan.
Thank you, Rosan. So, good morning, everyone. Today I present a paper called Doc-to-LoRA from our research team at Sakana AI, and the theme of our research is hypernetworks in the age of LLMs. So, I will mention a little bit about text-to-LoRA, our previous work as well today. Oops. All right, so today's frontier LLMs are amazing, right? We all know that, and we can do task-specific adaptation by just prompting or ask them to do agentic search, right? But they're still missing long-term memory or adaptation. And some would even say that these two cognitive capabilities are the blockage before we get to AGI. And in terms of practical usage, they do not learn from mistakes or user preferences from previous sessions. So every interaction feels like the first one, and the agent has to always go through your code base in case of agentic coding, right? So traditionally, these two problems can be tackled by updating the model. But since we cannot update the frontier models, um, the focus of our research is on local small LMs. So our long-term vision is allowing end users to adapt and specialize their local models to their needs. For example, personalization on personal data or memorizing the code base structure. So for instance, like if I have a local model specialized to my code base, the agent doesn't need to do agentic search every time you ask it to code something up, right? So the motivation of our work is coming from the fact that existing model update solutions are very slow and expensive, and very often they are very involved. And as a result, end users cannot easily adapt their local models. So today's solutions include Tinker API from Thinking Machines and Hugging Face Trainer, which many of you might have experience with. So it's also worth mentioning that OpenAI also has a fine-tuning API that is now being deprecated. And I would say that it is not an evidence that fine-tuning is no longer useful, but an evidence that existing solutions are already convenient enough for technical people to use. So if I were to fine-tune a model, I would go and build my own dataset, use Hugging Face SF3 trainer to tune my model instead of using a paid fine-tuning API, right? But the problem is that there's a big gap in terms of accessibility, speed, and cost in the fine-tuning regime, and that's what we want to tackle in our research. So traditionally, model fine-tuning is very slow, expensive, and we need to design a task, collect the data, label the data, and clean the data. And it also requires technical knowledge to maintain the infrastructure and the code around the fine-tuning workflow. So iterating on the traditional fine-tuning pipeline requires repetitive data collection and running fine-tuning jobs, right? And so everything is so involved that it slows down the experimentation speed. And another kind of model update we are interested in is factual knowledge update. So when a user provides a long document, for example, a PDF, the standard solution today is to put the PDF into the context window. This works but it means that every new query has to reread the same document, and it has to pay the full latency and VRAM cost each time. So, and since the PDF is in the context window, this approach breaks down entirely once the document is bigger than the model's context window. So an alternative is doing context distillation. So context distillation encodes new knowledge directly into the model's parameters and allows the model to access the knowledge without rereading the source directly. But this knowledge distillation process is very slow and computationally expensive. So before I tell you how we speed up the model customization process, I want to first make sure that everyone is on the same page. So I'll go through the background of Hypernetworks and LoRA briefly. So the original Hypernetworks paper came out in 2017 by David Ha during his time at Google Brain. So the concept of hypernetworks is a neural network that outputs parameter for another neural network. So you might ask, why do we want to do that? So there are two reasons. First is compression. The hypernetworks can be smaller than a target network. So we can optimize a smaller number of parameters. The other reason is the hypernetwork can do fast and cheap adaptation to the target model. So it can provide per task adaptation very quickly and cheaply with just a single forward pass. So a forward pass for a single input has two steps. The first step is weight generation. So here H represents the hypernetwork, T is the task descriptor, and theta is the parameters of the target neural network. And the forward pass of the target network that would actually process the input X is the next step. So in this setup, we assume that we can access the task descriptor corresponding to the input X, and this task descriptor can come from the dataset or the environment, or it can even be inferred by an auxiliary network. But in any case, we pass this task descriptor into the hypernetwork, which produces the theta, and our target network F is then parameterized by the theta that is produced by the hypernetwork, and it gives a prediction for the input X. So what I want us to focus on today is the fast and cheap per step specialization capability of the hypernetworks. And in our work, we want to use it for cheap modern LLMs customization. And another main component of our work is LoRA. So typically when we want to update or fine-tune an LLM, instead of updating the weights or the entire model, what people do in practice is only update the low rank matrices of the weights instead, right? And we call this approach low rank adaptation, or LoRA. And so here we combine hypernetwork with LoRA. So here in this equation, you can think of F as the target LLM, and H is our hypernetwork, and theta represent LoRA A and B matrices, right? And the task descriptor here could represent a textual description of a downstream task or a document that we want to update our LLM with. And how text to LoRA and Doc-to-LoRA work can be boiled down into this simple diagram. So the hypernetwork takes a task description or a document, and it outputs LoRA matrices. And these matrices will be applied to the target LLM. And what's nice about this computation graph is that everything is end-to-end differentiable, which allows us to use modern GPUs in our cluster effectively. So next I want to briefly mention our first paper in this line of work, text-to-LoRA. So text-to-LoRA tries to learn a hypernetwork that instantly outputs LoRA for downstream tasks given their task descriptions. So it avoids a traditional fine-tuning pipeline and removes technical barrier, allowing end users to fine-tune the model effortlessly, right? And instead of naively updating the model during deployment, our approach pay the update costs upfront by meta-learning the update generator that can be reused cheaply at deployment time. And the key procedure is to train the hypernetwork to instantly and cheaply generate compact LoRa adapters. And once trained, the hypernetwork acts as our update generator that produces task-specific updates for the target LLM on the fly. So here's a simple animation reiterating what I told you earlier. So here the question goes into the base model. It answers incorrectly first time, but given a task description to the text-to-LoRA hypernetwork, it produces a task-specific LoRa that can help modulate the base model to answer the question correctly.
May I ask a question, Tian?
Yes.
So the hypernetwork takes what you call that task description is just a string of text.
Right.
So it's sort of, it has a text encoder. It's an LLM, but it doesn't output text tokens. But it takes in as input text tokens.
Yes, so for text-to-LoRa, we use a simple text encoder model, and then we basically use the embedding vector of that text as an input to the hypernetwork. And the hypernetwork then produces the LoRa matrices.
Yeah. And the whole thing, the hypernetwork is trained while also training the original network with the LoRa adapter ways to perform the downstream task better.
Yeah, so the backpropagation goes through the base model, but we don't update the base model. We only learn the hypernetwork, and then we only update the hypernetwork and keep the base model fixed. And during adaptation time, we use the generated LoRa as the adapter to the base model, so that the base model with the adapter can specialize to the given task.
The LoRa weights are also trained, right? But it's an output of the hypernetwork, but it's also the weights are trained during fine-tuning. So
So the LoRa is actually the output of the hypernetwork, right?
right.
So the gradient goes through the LoRa, but we don't apply the optimizer to the LoRa. We apply the optimizer step to the hypernetwork only. Okay, thanks. So next I'll talk about the main paper of today, which is Doc-to-LoRA, and it was accepted to ICML 2026 this year. So very similar to Doc-to-LoRA. Very similar to text-to-LoRA. Doc-to-LoRA asks whether a hypernetwork can meta-learn the knowledge distillation step by mapping a document to a LoRa adapter in a single forward pass. And unlike the typical usage of LoRa, here in Doc-to-LoRa we use LoRa as a factual storage. And once the document is compressed into a LoRa, the adapted LLM can answer any number of questions without the document appearing in the context window again. So here's another animation showing what we are trying to achieve. A document and a question goes into the base model, converted into a big KV cache because the document is so big, which requires a lot of VRAM and slows down answer generation. And when a new question comes in, the KV cache is still there, which is then again slows down answer generation. But with Doc-to-LoRA, we first convert the document into a LoRa adapter, which can be used to update the knowledge of the target LLM. And once updated, the model can answer the subsequent questions without the KV cache of the document. So here's how the context distillation work on the per document basis. So given a document and a set of queries, we train an adapter that makes the LLM behaves as if the document is in context by distilling from the teacher signal from the same model that has direct access to the document. And the block on the right here is the teacher model, and the left here is the student that we are trying to train. The LM are actually the same model, but we can see that on the student side, it doesn't have the document in the input, but we have these internalized parameters, which are LoRA in our case, right? And then to match the laws, the LoRA has to represent the document, right? So this is how this is the idea of context distillation. But in practice, we are usually given only the document and not the queries during training. So for each new document, we have to generate a set of thousands of queries which are needed for distillation training. And this query generation step can take many hours on multiple GPUs. Then after query generation step, we have to go through the context distillation process, which is also very expensive and also require many GPU hours. And the most painful part is that we have to go through both steps every time a new document comes in. Right. So instead of so Doc-to-LoRA trying to meta-learn context distillation and map from document into a corresponding LoRA with one forward pass. So this explicit trade-off is the theme of our research. So we are willing to pay the meta training cost upfront, which includes query generation and distillation training across millions of documents. But then during inference time, we reap the benefit of the quick adaptation capability of the Hypernetwork. Right, so to summarize again, we pay the query generation and context distillation training cost during the meta training phase, and then the cost would be amortized across documents during deployment time. So the training is very simple. So effectively, the Hypernetwork learns to output LoRa matrices such that the adapted model in the middle behaves as if the document inside is inside its context window. So the training goes just like before, but now we backpropagate all the way to the Hypernetwork, and then we update only the Hypernetwork and keep everything else fixed. And again, as to Rosan's question earlier, we backprop through the LoRa, but we actually don't update the LoRa. We update the Hypernetwork, And since the hypernetwork keeps learning, the LoRa also keeps changing as the hypernetwork is learning as well. And is there any questions so far?
What you're describing is pretty clear. Is there a reason you wouldn't do like a mammal version of this instead of using a hypernet?
Yes. So our goal is to do cheap and fast adaptation during deployment, right? But mammal would require us to use few shot learning during inference time, right? And that can
No,
be very expensive.
so I meant mammal in the sense of just the model agnostic shape of meta learning. So there's two kinds of meta learning. So there is the hypernet based, and then there's the model agnostic. What you could do is like with this exact setup, but not have the hyper network and then just do a mammal shaped training, and that would adapt the LoRa instead. So that's what I was thinking.
Yeah, but then we only have one set of LoRa matrices, right? And then how would you per
Yeah, the hope
document
is
adapt?
that that is true. So it would learn a specific set of LoRa weights. Uh, but then the thinking behind mammal is that that should sort of be knowledge that is not specific to a document, but more like meta knowledge that lets you, extract the right bits of information, I suppose, out of any given document and or like any given pair of documents and queries. It might just be like this is just a stronger method. That's what I was thinking as well. But, I just wanted to know if you've looked at that at all.
Yes, so I think mammal it only trains a single set of parameters, right? And then
You will train a
that's
single set of LoRa weights, yes.
yes, and
Yeah.
then
The hope is that that set of LoRa weights lets the model, because at the end of the day, what the LLM is doing is it's doing some sort of reasoning, right? And the idea is it could just, so what you're doing here could have the LoRa weights remember very specific things about the documents, while if you did the mammal side of things, that could teach the model to sort of reason more generally across documents and queries, if that makes sense.
I mean, to me, this sounds more like continued pre-training or like fine-tuning general capabilities. And here it's really like adaptation that we want to get, right? And yeah, so I think it's almost answering a different research question, if you will.
Okay, fair enough. Yeah.
thanks, Robert. Um,
One quick question.
yes, please.
Can we add new documents every day, and so can we just accumulate knowledge in this hyper network? So one every day we do a new round with new documents.
Yes, that is possible. So the nice thing about LoRa is that they are linear in that you can basically add multiple LoRAs together to like combine knowledge from different LoRAs, and you can think of the addition operation as knowledge merge operation in the document space. So in our experiment, we will show that you can actually like stack multiple chunks of LoRAs together to answer very long documents.
Thank you.
Yes. So then I'll move on to the first experiment. So so then we want to test the
I
idea.
actually have another question. So I was trying
Yes.
to think about this setup of, so you're doing one form of PEFT, which is LoRa, right? Have you looked at something like prefix training to do this? Because if you did that, that could maybe generalize even to models that you don't really have access to, like that are not open weights.
We have that in the appendix of the paper as well.
Okay.
So we are experimenting with that.
So that's not, you find that to be not as effective as this?
Uh, So initially we didn't look at prefix training, but later we discovered that it's actually very effective as well.
Got it. Okay. All right.
Yes.
Thanks.
Yes. So in this task, we want to do a sanity test of how Doc-to-LoRA can work with a needle in a haystack task, where the model has to memorize a single needle among a noise text, right? And in this experiment, we want to show that Doc-to-LoRA can successfully induce knowledge internalization and enabling the base model to exactly recall the implanted information without reading the raw context. So we also want to show that Doc-to-LoRA can also bypass the context length of the base model, and this is a very impactful idea, since as I mentioned earlier, if the PDF is too long beyond the context window, this approach can be one of the ways to tackle the long context problem. And it also saves memory and inference time, since we no longer need the KV cache of the document, right? Okay, let me explain the training setup. So during the training, we use the input context length ranging from 32 to 256 tokens, and the training inputs are randomly chunked into 1 to 8 chunks, and each chunk produces one LoRA. If there are multiple chunks, we simply linearly add the LoRAs together. And during evaluation, the baseline model has direct access to both the haystack and the query. And for Doc-to-LoRA, the base model doesn't have access to any part of the context of the haystack, but it only sees the query prompt. And so the result is that Doc-to-LoRA accuracy stays near perfect up to 40k tokens, despite being trained up to only 200 tokens and using only 8 chunks, right? And yeah, on the right, we show that there's a huge difference between the memory usage. If you put everything in context, memory goes up very fast, and we can get out of memory error very quickly. But with the Doc-to-LoRA, the memory stays constant regardless of the length of the context, because everything is already compressed into LoRA matrices, right? And for real world use, this is very powerful, because users can internalize private documents once and then chat with the model without the memory overhead, and don't have to keep everything in the context window.
How does that relate to the rank of the LoRa that you're using?
Yes, so linearly adding the LoRAs is equivalent to stacking the rank of the A and B matrices. So say that you have rank 10 LoRA, two rank 10 LoRAs. If you linearly add them in the full matrix space, that would be equivalent to stacking the two A matrices in the rank dimension and two B matrices in the rank dimension. So that would be combining two rank 10 LoRAs into one rank 20 LoRA.
So, but then there should also be a relationship between the rank and the size of the haystack that it can remember, right? Do you see any patterns there where if you increase the rank, it could just, generalize to higher haystack lengths?
Yes, so here we use a predefined size for each chunk, and each chunk has only 1000 token,
Mm-hmm.
and So yeah, in this experiment on the left plot here, you can see that if we stack too much, then there start to be a degradation, and we show in the appendix of the paper, the camera ready paper, that this it has to do with the interference of the LoRAs, because when you stack multiple LoRAs, they can interfere, right? And then
Got it. Okay.
yep.
But that doesn't change at all with the ranks. I'm surprised of that because like if you just throw more rank at it and in terms of like actually the bottleneck size, right? If you just increase your R, wouldn't that let you stack more?
I think another point is that in needle in a haystack, the information that you need to compress is constant, right? Regardless of the length of the haystack.
That is true. Hmm.
Mhm.
Uh,
Yes,
okay, fair point.
yes, thanks for
Thanks.
that. Mm, yes, so moving on to the next experiment. Okay, so here we want to evaluate Doc-to-LoRA on the real-world reading comprehension benchmark. And here we show one benchmark, squad. So the performance on the y-axis is relative to the base model, and we compare Doc-to-LoRA against many baselines. So the training setup is we have 20 million unique contexts, and we generate 5 question answer pairs for each, and we do 2-stage training. We do training without chunking first, and then in the last 20% of training we chunk the input context randomly from 1 to 8 chunks, so that we can at inference time we can hope to generalize to more chunk than seen during training. And we use the pre-trained corpus for the training, and also we mix some question answering benchmark data into the training as well. And the evaluation is that we use questions and context that are not seen during training. So Doc-to-LoRA reaches 85% roughly compared to the base model. But here to emphasize again that Doc-to-LoRA doesn't have access to the full context, right? It only outputs a LoRA for the base model, and then the adapted model has to answer without the context. And we show on the middle plot here that we use less than 1 second for the adaptation process. And on the right, we show the memory efficiency, and we show that we use less than 10 gigabyte of VRAM for the model update, compared to 40 gigabytes of typical traditional context distillation process.
May I ask a question?
Yes.
Have you tried adding cross entropy to your loss function? I know you're using the softmax for the logits and also KL divergence. I'm wondering if you attempted to add cross entropy and if that would have any effect on getting a higher score for squad.
So initially in our experiment, we have tried using cross entropy loss, which we can definitely train a hypernetwork with cross entropy loss, but what we see is that it doesn't generalize well at all, and the answer would be very, so that the hypernetwork can easily overfit to the template of the answer that we have in the training corpus, right? So for example, if we train on question answering task, and then we ask the adapted model to summarize the document, the adapted model wouldn't summarize the document nicely at all. But if we
I
train with,
understand that you need the KL divergence as a regularizer, but you're using the softmax as the main loss, and you could have both.
right, so
How would that help though? Because you do have the cross entropy term in the KL divergence loss already, right? So it's not like you're adding more information, you're just reweighting the KL, I suppose. So I don't see how adding that could help, right, Michael?
I'm really not sure. I'd have to look into that.
yeah, there can be cases where the base model answer incorrectly, but we have the correct label. In that case, that could help in terms of task performance. But the idea here is that we want to maintain the behavior of the base model still.
Thank you.
Okay, any other questions? Okay, so moving on. So here's the part which I think is the coolest part of the paper. So in this experiment, we use a vision language model as the context encoder for Doc-to-LoRA, and we show in the paper that it allows us to transmit visual information to a text-only model. So the VLM process and input image and produces activations, which the hypernetwork maps into a LoRa update to a pure text model. And then the pure text model answers the question without ever seeing any images before, right? And in this experiment, we have to train a new hypernetwork because we switch out the context encoder.
You could probably do that with a projection matrix to go from the image into a text mode. I think that's generally what's done with vision transformers. So then you could use the same hypernetwork.
Yes, that's exactly what we are doing, right? So during training, we actually don't use any images at all. We only use the text, the same text data that we used to training in the previous slide. But during inference, we use the image encoder that that also has a projection layer here that maps visual information into the text encoding space, right? Which is then can be processed by the geometry model. And so the takeaway in this experiment is that we can transfer visual information into a pure text model, which I think is very, very cool.
So
And
what is
yeah,
the input to the hypernetwork in this case? Is it the output from the Gemma model?
yeah, so it's exactly the same as before, right? So we here the LM on the left and on the right here they are the same, right? But we effectively switch out this one as a VLM, and during training it only sees text input, but during inference we switch out document as a image, and then you use the cyclic encoder and then the modality projection that projects visual embedding into a text embedding that can be processed by the geometry.
So when you do the training, you're also using Gemma 3 then for the document embedding?
Right.
Okay.
So we have to train a new model for every context encoder and target model pair. So, and I think more broadly, this result suggests that Doc-to-LoRA could be used as a general context to LoRa mapping. And interesting research idea is to see how hypernetworks can become a modality bridge that moves information from one modality to another model's parameters in the style of model merging. And so since Doc-to-LoRA went out, I have seen two notable papers. One that encodes video into a LoRa, and the other one Robert just sent me before this talk, that they encode code base or code file into a LoRa as well. So this research direction, I think is very exciting. So yeah, so that's all I want to say about Doc-to-LoRA today. And is there any question about Doc-to-LoRA so far? We can take a few questions while the video is playing before I wrap up this talk with the conclusions.
Yeah, I have a question. Just would you see this also extending to just encoding the whole, like a whole conversation into essentially these weights as well? So like, for example, you wouldn't have to deal with a model getting progressively worse as the conversation gets too long or too extended?
Yes, so we know that context rot is a thing in agentic coding, right? And yeah, I'm looking forward to see this technique be used to also tackle context rot problem as well. And yeah, but during training you would have to train on the conversational data and coding data, right? Which is more expensive to collect, and but I believe that it can be used in the same way as how we train Doc-to-LoRa.
Understood. Thank you, Tan.
Thanks. No worries.
I also think that I personally find really exciting about the project that it kind of questions whether or not we need super large monolithic foundation models, or whether or not we spend a lot of compute on basically meta training these hypernetworks and then having small language models that we roll out, right? So in many ways, one could imagine that in ChatGPT overnight, you basically distill all the knowledge that was drafted during that day into a new version of the model, right? And I do think that sort of can unlock many new different applications.
If someone had to go like the hypernetwork route for agentic instead of doing compaction, how would you envision that? Like, and if they're doing LoRas, right? Would you basically have to like keep adding, like every time you really need to do a compaction, would you generate a new LoRa and add that back to the previous LoRa that you already had?
Yeah, so in our work, the way we combine LoRa is very simple, right? We just add them together. But there are active research in how to combine LoRas. Very sophisticated routing could also be possible depending on the context, right? You can choose which LoRas to activate depending on the context. Or you can overnight consolidate LoRas that are redundant, right? And I think there are so many active research questions that we can tackle in the next year.
Right.
Yeah.
Yeah. Now, I was just sort of trying to ask this based on the experiment. You've, of course, obviously played around with this quite a bit, so you might have an impression of what would be effective, I guess,
Right.
is what I
So
was trying to ask.
I guess going back to your prefix training question, right? So you can think of compaction as some sort of KV cache eviction or KV cache compression as well. So instead of doing in a raw text space in the usual compaction sense, you can compress in the prefix cache style, right? And that can even compress even more information because the prefix cache doesn't have to be natural tokens, right? You can add in arbitrary KV cache values, and that can be very flexible and more information dense.
Right. It's actually if you did. No, sorry, I take that back. I was trying to think about something completely different, so don't mind. And then for something like even with the prefix, I think my question still sort of is orthogonal in stance, in that you could, even with the prefix, you could do it two ways, right? You could keep appending the prefixes that you've, intermittently learned,
Yeah.
or you could combine them somehow, which in your LoRa case, it seems like you could just add them and that's effective, right? But yeah, that's probably still an open question too. Someone could dive into that, look at that.
Yeah, so as in the KV cache case, prefix cache case, you can even recursively compress the prefix, right? So you include the prefix in during the compression time. So the
Right.
next compression
Yeah,
also compress the already compressed tokens. Yeah.
that's true. Yeah.
Hi, I have a couple of questions. The first one was, what's the architecture of the hypernetwork itself? And the second question was, do you test with like contradicting or complementary facts where the original memory contains some fact and the LoRa is introducing something that's entirely different, and what the model prefers in that sense, in that case?
Yes. So the architecture of the hypernetwork is based on the perceiver architecture. So this is the overview. It's very dense, but you can think of perceiver as uh, a model that takes in variable length input. In this case, that would be the document, right? And it outputs a fixed size matrix. In this case, it would be LoRA, right? And the perceiver architecture is very flexible. It's very expressive. It has been shown to be very strong on various uh, really very multi-modality and long context scenarios, right? And then we simply picked this architecture because it is well known and it has been proven to be working very well. And so for the second question, um, we have tried that, but not formally. So in the paper, we mostly report benchmark results, right? And we have one experiment actually is in the paper. So in the paper, we also have one experiment that we simply ask questions that are not related to the context or the compressed document, right? And in that case, we show that there is a knowledge interference problem. So you can think of Doc-to-LoRA as we overfit the target model to the document, and if you ask the target model, the adapted model about something else, it would hallucinate information about the document instead of answering the question directly.
I see. Thank you.
I have a quick question about your headline numbers on figure 1 in the paper, like, could you maybe briefly explain that normalized performance on the comparison on those two tasks?
Yes, so here effectively we use the base model with context as the upper bound, which we use as a reference for being perfect score. And relative to this score, our model can achieve more than 80% of the original performance.
And the original performance, is it like just a LoRa fine-tuned on this task? Or?
Oh no, the original performance is the base model with the full context information in the context window.
I see. And does it even make sense to compare its performance to LoRa fine-tune on this task, or is it guaranteed to be the same by construction, like by the way you train it?
I think you're kind of mixing up the two papers right now, right? The text-to-LoRa paper and the Doc-to-LoRa paper. Sorry for that, I guess. But here, right, it's like we're meta training this hypernetwork to do context compression.
Yep.
And then in some sense, the fair baseline is to compare to the, or yeah, fair is, is always relative, but yeah.
Yeah, there's no reason you couldn't do like a fine tune, just a LoRa fine tune and use that as a second baseline, I guess.
Yeah, exactly. That's the question. Would it affect the performance, or like how would it be different to just using regular context distillation with LoRa one?
Yeah, I mean, the fact that this generalizes is probably it's going to be slightly better if you just fine tune on just the one document with the LoRa.
Yes, so
Yeah.
so that baseline is actually this diamond here, right? So this is actually a LoRa as
Right.
well,
Oh,
and
okay.
it trains on the target query and the target document. Yes.
Oh, I see. Thank you. Thank you for explaining.
I just had a question on just the understanding of the meta learning training procedure. So the way you're training your hyper network is you have your document that you care about, and also you've generated a bunch of queries and ground truth responses. You pass them through your meta network or the hyper network. It produces a LoRa. You add that LoRa, and then you only have the optimizer point to the hyper network's weights and not any of the other weights, right?
Right. Right.
So basically, I was kind of hopeful. I was kind of hoping that we wouldn't need to find like a ground truth query response kind of thing, because that takes the most amount of time to curate for every new document potentially. Especially, I was thinking in the firm that I work at, we have huge amount of documents, but then just finding those query response pairs is the most manual and most hardest part of the like I would say training corpus. So is there a way to like get rid of that, or at least like reduce the burden through this procedure, or are we just like front loading that in the hypernetwork creation?
Are you asking about the traditional way of training this, or during deployment of Doc-to-LoRa?
Well, I think it's traditional way of training, as well as just like, is there a way to like not, like I was hoping for not having to curate like a data set where you have like query and ground truth responses, and can we get away? I mean, in this procedure, it seems like you're front loading that to train your hypernetwork, and
Yes.
typically people would train like a specified model for each task. So I'm thinking, is there a way to not have that? Because actually generating that data set is in some sense, in some cases, is the very hard task, especially if you're like, if you have a huge number of documents, or especially if you're thinking of like even agentic coding, let's say tasks, and you want to add like LoRas in dynamically add LoRas to your inference, to your base model, then in that scenario, like the document that you're actually training on keeps changing because of the different repo that you're using, or potentially different kinds of things that you're adding, dynamically changing your document itself. So in that scenario, I would be curious to understand how would you like, is there a way to get away from that in some sense, or reduce the burden?
Yes. So if we want to train in a traditional way, instead of query generation, I think there are papers that try to train the LoRA or the prefix based on the reconstruction of the document itself. That way, we no longer need to generate the queries and the answer, the ground truth answer, right? Because the document itself is the ground truth, and the query is basically please recite the document for me, right? And they show that it can be very effective as well. But I think that depends on like how you regularize the training to allow it to generalize to answer questions about that document.
I guess another aspect is also that in the results in the paper, we show that we can achieve sort of, let's say, remarkable generalization. So like you said, we're front loading this, but we would expect that this then generalizes to new tasks, files, documents as well, because you're basically learning this compression operation.
Got it. Okay, that's good to know. Thank you.
The graph that you showed when answering Alex's question about like fine-tuning a specific LoRa to the document, the green diamond thing that you had, was that still with documents and queries, or was that just next to like language modeling on the document? The-
This baseline is knowledge distillation, but only on the exact document and the exact query
Got it. Okay.
that we are testing. Yes.
Got it.
We're over time, and to not let Tan stay longer, I think we should just stop here. Are you open to receiving questions via email?
Yes, of course.
Okay, cool. And Rob, of course, I'm sure the other authors on the paper would love to hear from you if you have more questions. Thank you all.
Thank you for the question.
Tan. Thank you for staying
Have
so
a good
late.
weekend. Thank you, Roseanne.
It's already weekend for Tan, so have a good sleep.
Thank
everyone.
Thank you, Tan.
Have a nice day, y'all. Bye bye.
Bye bye. Take care.